Okay, so I think we are live now. Good afternoon and hello everyone. So we are now in the first live session for this course, Game Theory and Mechanism Design. And in this past 5 weeks, we have covered a lot of topics. Before we start taking questions, maybe we can just go over that slowly and just to refresh your memories that what we have discussed so far. So let me just share screen. So in the first week was pretty simple. It was mostly about discussing different examples of game theory. So we discussed the game of chess and we proved the theorem about chess to give you an initial feeling about this what the game of chess is all about. And then we formally started discussing this game theory using normal form games. And then in normal form games, there are different concepts which we discussed in the second week: dominance, Nash equilibrium, max-min strategies, elimination of dominated strategies, preservation of PSNE when you eliminate dominated strategies, then matrix games, and then what are the relations between this PSNE and max-min in the matrix games. That was about week 2. Then we introduced a new concept called the strategy that can be mixed. So a probabilistic choice of strategies. So that is called mixed strategies. And very naturally, there is also an equilibrium concept associated with this mixed strategies, so which is called the mixed strategy Nash equilibrium. And then we so we saw that a result which says that mixed strategy Nash equilibrium exists and how to find the mixed strategy Nash equilibrium and their algorithms. And then later in this fourth week, we discussed correlated equilibrium, and then we formally got into extensive form games. So there are a lot of topics. I think we can go over these questions in any order. I mean, if you are finding any specific topic difficult, we can discuss that a little bit more. If you have done some problems and you are facing some difficulties, that you can also post. And so till fifth week, we have so far discussed the games in imperfect information extensive form games and the notion of perfect recall. But yeah, so let's go over these 5 topics as we see different questions. So please feel free to post questions on the YouTube channel, and I'll be looking at them and responding them. Dhanush asks one problem on PSNE in PIFG. Which one problem? So I just want to get a little more clarification about this question. So so you are talking about perfect information extensive form games and how one can find pure strategy Nash equilibrium in a PIEFG. So is that what you are asking, or how to find a PSN in that PIEFG? Okay, so let's take this first. So if I understand, so PIEFG, you know that that is a different representation of the game, right? So perfect information extensive form game gives you some sort of a graphical representation. So I think we have already discussed one such case in the lecture video. So just for your understanding, let me draw a similar thing. So maybe I hope you are able to see my screen. So there is these different actions available to a specific player. Let's say player one, and let's say player B is taking another action, another set of actions, and then maybe at the third level. So in this first level, player one is playing something, and in this second level, player two is playing, and maybe at the third level, player one is coming back again and playing another stuff. So maybe CD is the second level of strategies, a second level of actions available to player two, and then let's say E and F. And finally, at this leaf nodes, you get some utilities. And I'm just constructing this arbitrarily. I do not know what are the right numbers. Let's say 1 2 is the utility for player 1 and player 2 in this case. And here let's say it's 3 comma 4, um, 5 comma 6, 7 comma 8, something. Yeah. Now, the first thing when you are talking about finding the PSNE, you should remember that this PSNE is a notion in the normal form game. So somehow we'll have to transform this game into a normal form game representation. And for that, we need the strategies. So here we have only the actions at every level, but we'll have to first transform it into the strategies. Now you know that how you can find the strategies in this game. So you have this player one who is playing at this level and also in this level. So the the strategy of player one will be a kind of a concatenation of these two things. So player one can have strategies A E, so which means that it will play A in the first round and E in the second round, in the third round where it is playing, or AF or BE and BF. And similarly, for player 2, who is playing only once in this game, so therefore player 2 can have only two strategies, C or D. I'm just keeping this small so that I can handle it easily. So C and D. So this is the way we are transforming this extensive form game, perfect information extensive form game, into a normal form game. Now, once that is done, you know how to fill this up. So AE comma C means that the player one will play A and E, and this player two will play C. So that means, of course, it will never take this path because player one is playing A. So therefore, this utility will be 1 comma 2. So player one gets 1 and player 2 gets 2. Similarly, it doesn't matter whether the other player is choosing D because it is never going this path. It will be 1 comma 2. And similarly, AF, you can fill in these blanks. So I think everywhere it will be 1 comma 2 because A is the only determining factor. Similarly, if it plays BE, now it will be interesting. Now player one is playing B and also E in this case. And if player two plays C, that means it will take this specific path and the utility will be 3 comma 4. 3, 4. And if it plays D, the other player plays D, then it will take this path and this player's utility will be 7 comma 8. So you are just going to find the final outcome using this representation. And similarly PF will be 5 6, I believe, and this one D will be 7 comma 8 because here this it will never take this path because player 2 is playing D in this case. So now once you have this normal form representation of this of the PIEFG, now we can use the very similar thing how we can find the pure strategy Nash equilibrium. And the pure strategy Nash equilibrium is the pure strategy Nash equilibrium of this transformed NFG. So let's try to find out which one is a pure strategy Nash equilibrium from inspection. So, I mean, of course, you can use different techniques of finding pure strategy Nash equilibrium. But here by inspection, I can find that this is a pure strategy Nash equilibrium. Why? Because this number here is the maximum over this line, and this 8 is larger than 6. So this is certainly a pure strategy Nash equilibrium. So similarly, in the same way, this is also a pure strategy Nash equilibrium. Yeah, and I think there does not exist any other pure strategy Nash equilibrium. So there are two PSNEs in this game, and now if you extend this idea to subgame perfect Nash equilibrium, you know how to find that subgame perfect Nash equilibrium. You use this the backward induction algorithm. You start from the leaf and try to find out what is the best option that player player one should have played at this level. So if it was ever in this round, then it would have played F, because F gives, sorry, it should, yeah, so it should have played F, because that is giving it a little higher utility than playing E. So given that player 1 will be playing F, if it reaches here, what should be 2's best response at this round? So between C and D, if it plays C, it knows that player 1 will play F, and therefore player 2 will get an utility of 6. If it plays D, then it gets a utility of 8. So certainly this is larger, so therefore player 2 will play D. And given this fact, what should player 1 will play at this first step? If it plays A, then it gets an utility of 1. While if it plays B and then player 2 is known to be playing D, then it will get this utility of 7, which is larger. So therefore, it makes sense to play B. But now you can club these two things together, playing B here and playing F here, and then player 2 will play D. So this is going to be the subgame perfect Nash equilibrium, SPNE, as we said. And you can see that that is certainly a pure strategy Nash equilibrium, and that is one of this Nash equilibrium which is showing up as a predictable outcome when both these players are playing sequentially, and it is telling you something about the rationality that these players will be doing. So there is a follow-up question for Dhanush. BED, we have taken 7, 8. BED, right? Yes, we have taken 7, 8 rather than 3, 4. No, so because player 2 takes D, player 2 has taken C, then player 1. No, so the reason is that so when you are talking about this B, E, and D, look at the trajectory in this game tree. So player 1 has announced that I'm going to play B in this first round, and also let's say E in this third round, if it ever reaches that round. But here it never reaches that round because player 2 has already played D, so it never takes this path. So how should player 1 ever play this C or E or F, whatever it is? It is playing D, player 2 is playing D, and therefore we are reaching to this state, and that is the utility that I have written here. So that's the reason. Okay, so let's go to the other questions. So how to implement and experiment with the topics covered so far? Is this possible to include some tutorials in every week content or libraries meant for implementing game theory concepts? So, okay, so it's a good question. So I do certainly believe that if you write programs, then you will certainly understand these methods better. But there are very few libraries that are available. So you can find something, a tool called Gambit. Just Google for it. I think you will land on that page, which is about Gambit Game Theory Project or something. The good thing about this is it provides you a list of different ways how you can model the game. So Gambit also gives you a format. So, for instance, if we want to find out the pure strategy Nash equilibrium of a given game, the first question will come is how should you represent the game? So, Gambit has a format for at least for normal form games. Not only at least, I mean, it also has a format for extensive form games, which is a little more complicated. So, I suggest that you start with this normal form game representation, and I do not remember the exact details how this looks like, but typically it gives you several information like the number of players in this game, then the number of strategies per player, and then also it gives the utilities. So essentially all the things that we have discussed. So utilities of each player, and it has a very specific format. So the utilities, I remember that it has a one single line where there are several numbers which are representing the corresponding utilities, but you will have to read that file carefully. So you'll have to write a program how you should take that .nfg file as input, and how you can parse that file to find out how many number of players are there, how many number of strategies are there, and what are their utilities, so that you get that game representation. Once you have that game representation, now you can write programs to find out the pure strategy Nash equilibrium or mixed strategy Nash equilibrium. Because this course is like offered online, I did not give any programming assignments, but I think it is always recommended to do this kind of an exercise, and Gambit is a very nice place to start off. So yeah, so Gambit, of course, has this library, so you can use certain APIs for Gambit, which you can invoke and solve these games, find the mixed strategy Nash equilibrium, pure strategy Nash equilibrium, etc. But I would recommend not to use them to begin with. Write the code entirely from scratch so that you can understand every detail. In particular, when you are finding the mixed strategy Nash equilibrium, you will be using this the characterization theorem, through which you can find the mixed strategy Nash equilibrium. Coding that from scratch will require you to understand each of those steps of that characterization theorem, and that is something that I highly recommend. Okay, so that I think answers this question. All right. So yeah. So the next question is from Nikita. So says that with PSNE I was facing initial doubts. So what were those doubts, Nikita? So in the first game that we had discussed, so in the case of the dilemma, the prisoner's dilemma or the kingdom's dilemma game, there was two choices for each of these players: agriculture and warfare. And when both of these players choose agriculture, you know that they are going to get some payoff of 5. It is good. If both of them are choosing war, it is worse. But if one chooses war, player one chooses war, it gets much higher payoff, and the other player gets 0, and similarly this. Now here we had defined this concept um, of dominance, because you can see that no matter what the other player is playing, so if player 2, so this is player 2 and this is player 1, let's say, player 2 is playing A, then it is better for player 1 to choose W. And if it chooses W, then also it is better to choose W for player 2. So in some sense, W strictly dominates. So we said that W strictly dominates A. And this, of course, this is for player 1. That's what we have seen just now. But you can see that even for player 2 also, the same thing holds. So for player 1 as well as for player 2, this strictly domination holds, and therefore this outcome is somewhat the most predictable outcome. Now, this kind of a situation does not appear in all games, and we have seen one standard example where there were two friends, and one of them liked cricket more than football, and the other one likes football more than cricket. So, if both of these friends go together to watch a cricket match, then the friend who likes cricket, he gets more utility than the other one. But if they go and watch football, then the opposite thing happens. But if they go separately to watch two different games, then nobody gets any utility. So the idea of pure strategy Nash equilibrium is to essentially guarantee some reasonable outcome in this kind of a situation. Here you can find that there is no domination. So none of these strategies, none of this C or F dominates the other one, because even though this is larger than this, but this is smaller than this one. So so there is no domination of strategies. So what is the best guarantee that we can give? We can say that this outcome rather is a reasonable outcome, because now if this f comma f is chosen, none of these players have any reason to deviate. So neither player one, neither player two, they will always be in a local stable point, and from that stable point, nobody would like to deviate because it reduces their utility. So that is essentially the whole idea of pure strategy Nash equilibrium. So here we are talking only about pure strategies. We are picking either C entirely or either F entirely. So in notation, in mathematics, we have written this kind of a situation as the utility of player I when other players are picking a very specific strategy. So in this case, if we are looking at player I to be player one, in this case, then this strategy of the other player is F. So player two is picking F in this case. So I'm just also writing in parallel what is this F, and choosing this SI star, which is the recommended strategy, that is this F comma F, should be at least as much as the same the utility when it deviates and picks something else, when the other players are still choosing the same S minus I. So here you can think of that F comma F. If player one deviates and chooses C, and while the other player is still choosing F, this is going to be larger. And similarly, this holds for the other player as well. So of course, this is for player one. But if you go to for the utility of player two, so let's say U2. Now we'll have to look at the movement of the second player. So player one is picking F, and the other player is also picking F. This is larger than picking uh, F comma C. So this second player is now deviating to C, and that is not getting him any rather larger utility. So that utility is so this inequality holds, and also this inequality holds where player one is deviating and here player two is deviating. None of them are better, so therefore this is a locally stable point, or what we call the pure strategy Nash equilibrium. Well, so I do not know. I'll have to check with the NPTEL. So this is regarding this R-Goyal's question that conduct the next session through Zoom or WebEx. Yeah. So weekly problem solving sessions, that I'm not sure whether that will be possible, because then. But you always have this Piazza available to you. So if you have any, so I would. So one thing I want to make clear is that there won't be any sort of problem solving from my side. If you solve problems, and I have already given the problem sets, one of the um, posts in Piazza is only about practice problems. Those are the practice problems from the exercises of the main textbook, the Mashler's book. So if you do those problems, I highly recommend that you do. And if you find problems in solving them, then you post on Piazza, and certainly we'll see how we can help. We can either discuss them in a live session, or we can answer them in Piazza itself. But we'll not be giving problems as well as their solutions. That is not how this is going to work. So coming back to that question, Dhanush, is it clear now this idea of the subgame perfect Nash equilibrium and the PSNE in the PIEFG? So yeah, so it is coming back to the same kind of a thing. Yes, we can have more frequent interaction session. Of course, that is possible, but it is not about just problem solving. It is about what problems you have solved and what problems you have found difficult. Like this kind of clarifications, the things that you are confused about, or maybe you have already tried solving some of these questions and couldn't solve it. We can certainly address those questions. So what about the other topics? So yeah, so what about the other topics? So far we have discussed only pure strategy, Nash equilibrium, but mixed strategies or correlated equilibria. Do you have any questions on them? Okay, that's good. So mixed strategy Nash equilibrium is typically a little harder thing than pure strategy. So I'm glad to hear that there were no difficulties on that. So, to all the participants who are joining live, so how many of you have actually solved problems from the Mashler's book, and of which chapters? So nobody solved any problems. So you'll find your assignments easier if you solve problems from that book. Subjective is in. So the assignments are mostly problem based. So if you mean that as objective, then yes, it is objective. And if you mean by subjective, that is um, writing a lot of text. So I don't think that that is going to be the case. So uh, the assignments or even the exams are trying to test you whether you have understood the concepts or not. And problems are the best way of testing that. So yeah, so that's what I meant. No, so I think there was a difficulty in grading, and I know that some of you had difficulties, even though you have written some correct answer, in principle correct answer. There was this auto grading thing which did not run correctly, or it took a different string as input, and therefore it marked it as wrong. That is the reason why we have actually moved to upload file style assignments, um, so that you can just write your answer on a piece of paper and upload it by scanning or taking a picture. But that does not change the pattern of the questions. It will still be the same problem solving kind of a question. So let me ask you some question. Um, so on the screen you can see this game C. Uh, so this is essentially uh, right. Yeah. So Dhanush, I'm coming back to your question in a minute, because I already thought about discussing this. So this game C that you can see here. So what kind of representation is this? Is this a normal form representation? It's a extensive form representation. Any of the participants, can you answer this? No one? So consider this is your problem solving session. Uh, so this is the problem that we are solving together. So tell me what is this game C? Okay, it's an extensive form game. All right. So now let's try to reduce this into a normal form game or a strategic form game. So what are the strategies that each of these players have? So what are the strategies that player one has? We now know the extensive form games part as well, so we should be able to answer this. Player one strategies T1 and B1. Why? So what is a strategy in an extensive form game? So if I tell player one that its strategy is T1, will that give the complete plan of player one uh, whenever it is a player? So see that these are these places. This my mouse pointer is visible. So this places where player one is playing, and also player one, wherever this node has a specific number inside, that means that particular player is playing. Similarly, player two is playing here and here. So if I just say that player 1 is playing T1, will that completely tell me uh, the whole plan of player 1? Because player 1 is playing here as well as playing here. So with that, would you like to update your answer? Player 2 has B2, B1. Okay, so you can represent it in multiple ways. B2, T1, T2, B1, and T2, T1. Yes, okay. So yeah, now you get it. Player 2 is playing in these two places, and strategy like uh, T2, T1 or T1, T2 is essentially telling that this player 2 will play at this node, it will play T1, and in this node, it will play T2. Fair enough. Now, for player 1, it should be a Cartesian product of T1, B1 and T2, T2, M2, B2. Right. So this is a Cartesian product you can write in the same way that you have written for player 2. You can write T1, T2, T1, M2, T1, B2, and so on, right? So there will be 6 possibilities. Now, if we want to represent this game as a normal form game, then we have these strategies, the 6 strategies for player 1, and those 4 strategies for player 2. It will be a 6 cross 4 uh, matrix, which will give you the whole representation. Here, this problem does not tell you what are the corresponding utilities, so it does not tell you what are the utilities at this A, B, C, D. But assuming that there exists some numbers, something similar to this 12.6 or 9.3, you can fill that whole matrix and you can solve and find the pure strategy Nash equilibrium of that game. Right? So okay, so let's now move to this second game. Let's say game D. What happens there? Can you write down the utilities as you did, the strategies as you did in the previous case? So just to emphasize that this node, you can imagine that it's like nature. Let's say there is no player, either player 1 or player 2, who is playing here. So maybe the nature is tossing a coin and deciding which game should be played or which direction to go. So if the nature chooses, let's say, earthquake, maybe that's one nature's choice, or flood, then the players may have different strategies and different actions and therefore different payoffs. And if it chooses flood, maybe a different choice happens. So here the idea is that this nature's choices the players do not control, but if they are in this game, they will have a strategy ready. So for instance, you can imagine that a specific player may have a specific strategy ready if it is a earthquake, what to do, versus if it is a flood. So you can imagine it in that way. So now player 2 is playing in these two places. So what is the strategy set for player 2 in this case? Will that be same or different as in the previous game, in game C, for player 2? Yes, for player 2, Cartesian product of this thing. Exactly this is the Cartesian product that you have taken in the previous case as well. So T2, B2, these are the two actions available in the second state of this game, and similarly T1, B1 are the available actions in the first state of the game where player 2 is playing. So yes, T1, T2, T1, B2, B1, T2, and B1, B2. These are the 4 possible strategies. Now for player 1, it's pretty simple. It plays only in one state of this game, so therefore T2 and B2, those are the 2 strategies. Okay, so similarly, now we are extending to some situations where, this is a specific game. Well, you can do the same exercise for player game E as well. But because this is a little larger game, therefore I don't want to get into that. So let's look at game F, and here you can see that this particular player, so player 0, who is something like a chance player, it is taking randomized outcomes. So you can imagine that this player is like a nature player, and therefore if it chooses a specific outcome, so if it chooses this half and half, so it is not choosing a specific action, rather it is picking both these actions with probability half and half. You can think of this player 0 is choosing a mixed strategy. um, so yeah, all these problem sets are already shared on Piazza, so yeah, I don't know why you haven't seen that already, but problem sets are already shared. So now you can represent the these actions, your corresponding representations slightly differently. So can you tell me what will be the strategies for player 1 in this case, in game F? So I'm giving you a hint, and I'll not give you the complete answer. So here, because there is only one player, so player 1, 0 is just a chance player. So your strategy for player, the strategy set will still remain the same, T1, T2, because that strategy is telling what are the possible options or possible plans of player 1. So if player 1 is in this node, then it will play T1, and if it in state 2 it will play T2, that will be encoded into the strategy called T1, T2. So that is going to be the same thing. Similarly, T1, B2, B1, T2, B1, B2. But now, when you have when you talk about the utilities, so now there is no other player. So utility of player 1 at a specific strategy, T1, T2, let's say. For that, you will have to find out what is the expectation of this utility. So even though player 1 is picking, so let's say I do it for just player 1. So player 1 is choosing T1 comma T2. That's the strategy for player 1. But then it does not play T1 all the time, because the nature chooses only with probability half this particular path of this game. So therefore it gets this utility 4 comma 8 with probability half. Similarly, it gets 8 comma 12 when it picks T2, that also with probability half. So therefore, the expected utility of player 1 when it plays T1 comma T2 is half times this 4 comma 8 and half times comma 8 comma 12. So the utility, the first component is for player 1, so therefore you can think of this to be just half of 4 plus half of 8, which is 6, I think. Yeah, 6. So similarly, you can find out when this player is choosing B1, then it also has a probability of choosing this. This second player again chooses this the outcomes probabilistically. So then you can multiply these two things together. So half times half, and then this, half times this, and then this rest half is here. So you can find the expected utility. So that is one way of solving this. You can solve a very similar exercise to find out the exact utilities. Now there is one chance player, which is 0, but this 1 and 2 are playing multiple times in this game. So therefore, you can find out what is the expected utility of player 2 and player 1 in this game E. Right. And yeah, these games are really very large, but I think at least you can discuss this game G. So let's say we are now focusing on game G. Uh, so what is this not sure thing? Which part you are not sure? Uh, Dhanush. Is it regarding this game F or game G? Oh no, so it is not about the mixed strategy. It's still the pure strategy, but the utilities are sort of randomized because the game outcome is random. So okay, so let me just explain this in on the Jamboard a little better. Uh, Draw this diagram and then come back and explain this. So 8, 12, 12 feet, right, and 9, 12, 3, 6. And this one will probably half and half. So it's also probably half and half. Okay, so let me share this. So this is the game that we are looking at. Uh, so this was T1, this was T1, and I think this was T2 and so what I was saying is that player one, so the strategy set of player one is consisting of four strategies, so T1, T2, T1, P2, T, sorry, uh, then P1, T2, and P1, P2. So these are the four strategies, and this player zero is just a chance player, so we don't really worry about that. So we are only worried about this first entries here because that is the utility of player one. So how should we write the utility of player one when its strategy is, let's say, T1, T2? That is the question that I was asking. Um, so if it is T1, T2, then we know that uh, it gets a utility of 4. Player 1 gets a utility of 4, but only with probability half, because with probability half, this 0th player or the nature chooses this particular branch of this game. So this player 1 does not get 4 completely. It gets this 4 with probability half. Right? That is the meaning. Similarly, it chooses T2, but it also comes to this state of the game only when this choice is made by the gets 8, not exactly, but with probability half. So 8, 12, I think the understanding, the description is coming just from the previous game. So there is some utility for player 2, but player 2 is not playing anywhere. So if you want to think about player 2, you can also compute the utility of player 2, but player 2 does not have any strategy in this game. Or you can think of well, it does not really matter. So if you consider player zero's utility to be the second player's utility, you can also compute that. That is also a possibility. But here, by this half and half, it means that it is choosing a strategy of half and half, and there is no other strategy for the other player. So that's why it is called zero. It's not a real player, because real players are numbered starting from 1. um, so I'm ignoring player 2 here. The second entry everywhere is ignored because that is not part of, it's not playing any role in this example. Only player 1's strategies are meaningful. So you get this. So this is 6. While if you are talking about the utility of player 1 when it is playing, let's say, B1, B1, and let's say B2. So then what you will have to find out is if it plays b1, then it gets this utility 9 with probability half and 3 with probability half under this situation where the first level has been chosen with probability half. So in some sense, half times half, it gets the utility of 9, plus half times half, it gets the utility of 3. This is only coming from this branch. Let me color it in a different way. So it is only coming from this part of the branch that we have discussed here. So these numbers are coming from there. And if you have this, the other part where it is coming from this part of this numbers, it is only playing B2 in this case. So it will get some half times 12, right? Whatever that number is, that is the expected utility. Similarly, you can find out the utilities for all these 4 possible strategies of this player. Okay. Yeah, maybe I don't know exactly what the numbers are. 12, 3. Yeah, 6 plus 3, 9. Yes, it is 9. Okay, so yeah, so I highly recommend that you do these problems from this book. They are really very interesting. So yeah, so game G, what I am going to tell you is that now you know the incomplete information, imperfect information extensive form games, right? The IIEFG. So, and this oval shaped diagram is telling you what are the information sets. That means this particular player, so player 1 here cannot distinguish between these 2 outcomes. And similarly, player 2 cannot distinguish between any of these outcomes, any of these nodes. So, and that is the reason you see that in every information set, the same player has the same set of strategies. So you can see that TB is the same strategy everywhere. So you can find out what are the possible different um, uh, what is the normal form representation of this game, right? Normal form representation, you can, I mean, you can figure that out. Player 1 only has 2 strategies T and B. Player 2 also has 2 strategies T and B, and it's a 2 player with each player having 2 strategies. But the utilities is not very easy to find out because there are this chance player, this nature player, who is playing probabilistically. So therefore you will have to take this path. So whenever this player is choosing T, what is the expected utility that it is playing, it is getting, because it can get either through this T, through this path with probability half, or it can get this T with the probability half through this path. And if it gets there, then if 2 chooses T or B, depending on that, you will have different utilities. So it's a very interesting example. You try it. If you cannot do it, then we can discuss it in the next session. Okay. So I think we are running out of time. So we discussed quite a few number of examples and also um, conceptual things. But I highly recommend that you do all these problems, and next time come up with some problems where you have found difficulties. Post them on Piazza, because these games, sometimes these game representations are so long that it will take a considerable amount of time for me to read and then solve the problem. If you post ahead, then I'll know which problems to solve, then I can go quickly over those problems and those examples, and make use of Piazza as much as you can. Okay, thank you.